Hey everybody, it's Finn from the Cold Lake First Nations Lands and Resources Department. Today I'm going to give a presentation about water levels in Cold Lake. The presentation is designed to help people understand a little bit more. We have had a lot of people, talking to us about, levels in Cold Lake, and I wanted to just put this together so that everybody has a good understanding of, the issue, so we can talk about some other things like the water line and other potential impacts. So we know that people are concerned about this. We also know there was a regional water line system that was just connected to Cold Lake, and people are concerned about that impact on the lake level. And like I said, we want to make sure everyone's informed about the issues in Denny and that people can come to a good understanding about what is significant and what to watch out for. So next slide, please. So first, we're going to start with an overview of the drainage basin, and then we're going to talk about what's called water balance. So that's how we would look at the stocks and flows of water. Where does it come from? Where does it go to? We're going to talk about water withdrawals. How many are there? Who withdraws? How much? Climate change, and then the impact of water withdrawals on water balance is ultimately what we're going to get to here. So next slide, please. So the Cold Lake watershed is quite large, and actually most of it is in the Clar. And so you can see that Primrose, the area around Primrose, is really what feeds, most of Cold Lake. So even down on the southwest side of Cold Lake there, you can see really not much of the area actually drains into the lake. Most of it drains into the Beaver River. So it just is a lot different sometimes spatially than people sort of really comprehend. The watershed is very large. It is also very remote. So most of the area around Primrose is a lot of muskeg bogs. It's very different than, the area we're sitting in now. And the other thing I want to point out here is the gauging station. So at the city of Cold Lake and at the outflow of Cold Lake at Cold River, there are these gauging stations. And so those record the level, and in the case of the Cold River station, it also records flow. And so these stations have been around for a very long time. They have data records that go back to the 50s. Anyone who wants to can access this information. There's an app on the App Store called Alberta Rivers, AB Rivers. You can install that on your phone. You can look at the current water levels. You can look at the annual trends. You can see a bunch of data. It's a really cool app. Anyone who wants to, can go and just grab that and have a look at it right now. Next slide. So I want to introduce this concept of water balance model. So a water balance model tries to account for where the water comes from and where it goes in a system. And the key factors in a water balance model are evaporation, rainfall, runoff, stream flow in and out of the lake, and then groundwater gain or loss. And so we're going to talk about all these things, but on the right side here is a picture that's sort of a schematic that has some numbers attached to it. This is from a 2006 study of the Beaver River Basin, so you can kind of see it like focuses on the Beaver River as opposed to the Cold Lake drainage basin. I just threw that up there to sort of give people like an understanding of how we're going to talk about these things being quantified. Next slide, please. So let's talk about historical water levels in Cold Lake. So this graph here shows the water level over time up to 2016, when this report, I just grabbed this out of a report. So you can see that, so the current water level, I just pulled this off the Alberta Rivers app on the weekend. So it's 534.8. So the lake is this low from a meters above sea level perspective, quite frequently, almost like most years. Going from 2016 back to, say, 2003, it does kind of approach these levels. The lake level has swung a lot before in the past. Like if you look at the 1996 situation, it was gaining lots of water, and then just one year just lost tons of water. I don't have an answer for why that was. But you can see that, what's happening, 534.8 is not, it's not a crazy number. Like that level of the lake is actually, relatively speaking, normal. I want to just highlight the yellow and the red lines on this graph. So these are called license cutoff levels. All of the permitted withdrawals have a cutoff limit. So when the lake level hits the yellow line, they have to reduce to 30% of their nominal withdrawal. So if they're allowed to take, they have to knock their withdrawals back 30%. So if they're allowed to take 10 cubic meters a day, they have to knock that down to 7. And at the red level, all non-essential water withdrawals have to stop. Any sort of permitted withdrawal from the lake is governed by these two sort of numbers, and you can see they do get hit, right? So those numbers are relevant in terms of license level. How low the lake is does affect what water licensees can do when they can take water. Next slide, please. So just because we hear a lot of questions about this, and also it's really cool, I want to talk for a second about groundwater. And so this region has got a lot of sediments on top of the bedrock. And this is a schematic, a sort of cross section that goes from like out by Wolf Lake over to, through Murray Lake and then across into Saskatchewan. And so what this is showing is the different the different geological formations and how they intersect with the lake. So you can see some of them intersect with the lake underneath where the lake is deep, and then thus they contribute water to the lake. And so Cold Lake is what's called a gaining lake. So that means that in an annual basis, it receives water from the groundwater. That's not true of everywhere. Murray Lake, I'd have to check. Murray Lake is probably a losing lake. If you see there, you've got like that, you can see how Murray Lake is perched up a little bit higher than Cold Lake and has some aquifers that connect in between Murray Lake and Cold Lake. So probably Murray Lake, is a losing lake. It's important to know that just to say, like, we recognize this is an issue. We're going to get to the quantification in a second here. So next slide, please. And also, just because I think this is a really cool slide, this is the Beaver River area again, but this shows the bedrock topography. And so what the lines on there are showing you is actually these deep channels that are old stream channels in the bedrock. And, we don't see these on the surface because they're covered in like hundreds of meters of till and other geological formations, but they're down there. Like there are sort of like underground old river channels that, mean that aquifers are discontinuous. Sometimes they're there, sometimes they're not. Sometimes they have water, sometimes they don't. There's a lot going on under the ground that we can't see. Next slide. So let's get into the wonderful world of water balance modeling. And I know this is a big wall of text here, but we're going to go through it in what I hope is, a reasonably understandable way. And so the water balance is really driven by a bunch of different factors. So you can see here we have precipitation, we have net inflow, we have evaporation, we have groundwater, we have withdrawals. So that would be all the water pipes, so Imperial, CNRL, the city, and we have outflow. And in the end, this shows change in volume. This is from a 2017 Stantec report. I just clipped these 10 years of data, so 2005 to 2015, because they were complete. The water balance model ran backwards. It just didn't have a bunch of accounting for the water withdrawals in there, so I didn't use that. But I just wanted to demonstrate to people, a couple of things. So first of all, if you go look down on the average level, so you can see here, I want to point out the average water withdrawal, 5.97, and these units here are million cubic meters or cubic kilometers. So that's a huge amount of water. 1 million cubic meters. So just to put that in context, the water trucks that CLFN has are like 7 or 8 cubic meters. And so here we're dealing in the hundreds of millions of cubic meters. So the total withdrawals are 6. And so I want to compare that to the average inflow for the year of 673. So, or the outflow, for example, which is about 600, or the evaporation, which in this case is average of 253. So, total water withdrawals from the lake are very, very small relative to the amount of water that's just moving around naturally in the water cycle. So when we look at the other thing I wanted to point out was to try to convert this into some units that are a little more understandable. So inches. So let's think about it in inches of lake level. So precipitation accounts for about 1.8 inches in lake level. Inflow is about 7.4. So if there were no flow into the lake in a year, it would drop 7.4 inches. Evaporation, so 2.8 inches of water just evaporates off the lake every year. And then we look at the water withdrawal, which is 0.07 inches. Is that 1 or 7? I can't see. 7. Call it 7. 0.07. These numbers, although like water is withdrawn from the lake, the amount of water withdrawn from the lake is like really small compared to the sort of normal hydrologic function. The other thing to point out, I thought this was kind of cool, was the change in volume. So over these 10 years in this model, the lake actually gained about 1 cubic kilometer of water. That just happened to be where it was, like we saw in the lake level, that this stuff swings over time. So this just happened to be 10 years where it gained a little bit. That gain resulted in 0.01 inches of additional water. So not even enough that the average person could even see. I guess just as a sort of, disclaimer, you're going to hear me talk a little bit about like uncertainties. So we'll talk about this more at the end, but, net inflow, a lot of this stuff is calculated. This model was built and then parameterized by running it backwards effectively, so showing that it could accurately predict lake level. But this is not, the basin is not well instrumented, so we should think of this as having some variability in the real world values. The important thing is that this model was able to predict and quantify, you know, the where the water was going and where it was coming from. Next slide, please. So let's talk for a second about the implication of the water line on water balance. So how big a deal is the water line? So withdrawals are supposed to rise to about 6 cubic kilometers by 2032. And so this is really a function of population growth. And so you can see on the top right there, I have this table that shows projection. And so basically what it's saying is that the average amount of water used by a household, that's going to stay stable, but the number of households, or the population effectively, is going to go up between now and 2032. That's the sort of source of the rise. And on the bottom table here, so these are actually in different units, so watch your units in math, right? So this is in cubic decameters, so we have to multiply by 1,000 to get to cubic kilometers. But you can see that Cold Lake Regional Waterline typically is responsible for like 2.5 to 3, you know, a year. Canadian Natural withdraws like, you know, 0.2, 3 cubic kilometers per year. Imperial Oil is the bigger user in the lake here, you know, between 2 and 3, you know, cubic kilometers a year. So those are the major other withdrawals. And so put in that context, the water line isn't bigger. It's kind of about the same size as Imperial. And we're going to talk about the sort of future of that in a second here. So I guess the point on this slide here is that, like, the water line is going to, you know, result in a net increase based on historical information. It's going to result in a net increase in withdrawals, but as we can see from the water balance, that amount is really pretty small, you know, compared to the natural flows that are moving around in the system anyways. So next slide. So why are water levels low this year? So we know they're low, but they're not really outside the normal range. Like when we looked at that graph of the historical lake level, it isn't actually crazy outside the normal range, but we are experiencing drought conditions, like pretty substantial droughts. So this is a map from August 31 of this year, 2021, showing drought status across Canada. And you can see that most of the prairies are in extreme or exceptional or severe drought. Like that's what's going on this year, is they just have not had a lot of rainfall. And as we know from, you know, the models, or the sort of water balance model we looked at earlier, you know, precipitation drives a lot of what flows into the lake. So if the Martineau River is low, the lake level is going to be low. And that's just kind of the math in this basin, is that really there's only a very small amount that's contributed to by groundwater. Although it's not nothing, it just is not a huge amount that comes from anywhere other than, you know, precip or runoff from the Primrose Basin. So next slide, please. So I wanted to talk about climate change here, just because it's always a good time to talk about climate change. So climate change projections are just phenomenally complex models. They make your average weather forecast look like long division on a napkin. But there are really accessible ways to access some of this stuff. So Alberta Climate Records is a great site, and it's run by some people who were formerly out of U of Lethbridge. Really cool site, and it actually shows you a bunch of ways to, you know, play with the, you know, projections, current versus historic. So I was just messing around with it when I was putting this together. And so compared to 1951, in this area, we're already at about plus 2.5 Celsius. And by 2070, that number is projected to be up another 4C. So relative to 1951, in 2070, we'll be up at like 6.5 degrees on average warmer than it used to be. And we know that evaporation is a big part of where the water's moving around in the basin. And so this increase in evaporation could drive, you know, or increase in temperature could drive increases in evaporation. Now, the equation to calculate evaporation is more complicated than just temperature. It has to do with wind speed, relative humidity, and barometric pressure. But just know that, like, that's one way that, you know, climate change could affect it. Precipitation, on the other hand, which would be the balance here, it's very difficult to forecast, but the forecasts are actually, I was very surprised when I looked at this, even under, like, you know, very ranging scenarios, they all increased in this region. So the climate change predictions are for an increase in mean temperature, and then also an increase in, the amount of precipitation falling in the basin. And that is a very complex balance. I think it's pretty safe to say that it's not really clear what will happen, but at least it looks like it's not all on the one side of the ledger towards warmer and drier. If you're concerned about the low lake level, you should be concerned about climate change for sure. But to the degree that these models are able to accurately tell us what things are going to look like, I think we're still a ways from that. There's a lot of variability, especially in the precipitation numbers. Those are very, they have big error bounds around them. Next slide, please. I think the other way to think about the impacts of climate change on the basin is on, human use dimensions. So most of the industrial water withdrawal comes from older SAGD facilities. So that's Imperial's older plants like Lemming and McKeesis. A combination of age and economics, so either the price of oil or carbon tax, means these facilities will likely be decommissioned at some point in the not too distant future. So that will result in a net loss of withdrawals from the lake. So Imperial will stop withdrawing a bunch of that water because they no longer need it for these old legacy SAGD plants. The other thing that could be significant, because remember we talked about the water lines, projected growth was driven in fact by population, not by, changes in household use level. So if climate-driven migration starts to change population growth rates in regions like this, and I'm not saying it will, I'm just saying that's the sensitive number here in terms of like the withdrawal levels. It's how many people live in the region. If that number goes up, then obviously that would throw off some of these projections. But the one I think that people should be most, thinking about, especially in this year when there's like, the MD has declared an agricultural disaster. Irrigation for growing crops is something that's currently not done, as far as I can tell, on the water line as it currently sits. But if you want to think about, well, what types of things could happen that would really start changing the levels of water that are withdrawn from the lake, my number one pick would be irrigation. Irrigation can be pretty inefficient. It depends on the type. Pivot irrigation, we don't have canals or the types of irrigation district infrastructure that occurs in southern Alberta, but not impossible. So that I just sort of threw this up here just to talk about what are the possible implications on withdrawal levels. And, like really those are the ones I see as sensitive. It's population growth rate, and then whether or not you're irrigating, I think are the key ones to be paying attention to. Next slide. Okay, so let's wrap it up. Most of the watershed that feeds Cold Lake actually in the Clar. It's not around you, and it's a very different place. It's muskeg, and it's really remote. Water levels in the lake are closely linked to rainfall and evaporation. Those are the key drivers of water balance in the lake. There is water being withdrawn for human use, but it's very, very small relative to the other flows that just naturally exist. So nobody should take that as meaning, well, humans can't change the level of the lake. It's just like, we're not doing it yet. Right? Like the amount of water you need to withdraw to have a meaningful effect on the lake is astronomically large. It's in the hundreds of cubic kilometers. Climate change is likely to have an impact on the lake levels in the future, but honestly, it's not clear what the direction or the magnitude of that effect will be. So is it going to be a big effect? Is it a small effect? Is the lake going to get higher or lower? I don't think that there's a lot of certainty there, at least not from the models I've looked at. And then climate change is likely to cause human behavior to change as well. So potentially putting more pressure on water withdrawals. And those are management decisions that are going to be made over, probably decades. And I think are maybe relevant to continue to pay attention to for those who are very kind of, focused on or worried about the lake level. So next slide, please. Okay, well, that's it. If you have any questions, Daniel's going to put this up here. Maybe we can have people respond or ask questions in the comments, or they can reach out directly to me if you'd like to know more. Thank you.